Okay, so just to remind you, I didn't even move the screen here. This is where we left off. We had this kind of big equation for power here. And we have this capital P times capital P cosine 2 omega t minus Q sine at 2 omega t. So we're going to move on here and kind of see how this is helpful to us. So what we're going to do is we're going to actually compute the average power. Now, something you should remember from calculus that the average value of a function is 1 over b minus a integral from a to b f at x dx. You should remember that from calculus. Now, we have to be a little bit more careful because we're not talking about a specific interval. We want to know the average power of this function through all time. So there's a slightly more mathy definition for what the average power is. But I'll give you the main result here. So for a periodic function, the average value is simply 1 over the period integral from minus t over 2 to t over 2, so integrating over a period of your function, and I'll put it, because we're doing it in time, f at little t dt. Now you might say, why did I do negative t over 2 to t over 2? Well, there's a very good reason why. I'll do that in a second here, which we'll get to. But what we're going to get here is we're going to go ahead and do this integral, or at least kind of go through it here. Sorry, lost my train of thought there for a second. So what we're going to have here is we're going to look at the period as being equal to, or not the period, the average power is going to be 1 over my period times the integral from minus t over 2 to t over 2 p plus p cosine of 2 omega t minus q sine of 2 omega t dt. Now, we're going to do this actually pretty quickly, this integral. It looks like it's an ugly integral to do. It's not. It's easy. So first off, when we're doing this here, let's just split this apart here. So I'm going to look at 3 different integrals. So I have 1 over t, integral from minus t over 2 to t over 2, capital P, plus integral from minus t over 2 t over 2 p cosine of 2 omega t dt minus, whoops, I forgot my 1 over t there, 1 over t integral from negative t over 2 to t over 2 q sine of 2 omega t dt. Now, I claim one of these is very easy to do. This one I claim is just obviously 0. And how do I know that's obviously 0? Well, remember, if you have an odd function, which is what the sine function is, it's an odd function. Well, if it's an odd function and you have the integral from minus a to a, f at t dt, that's equal to 0. And the sine function is odd. So I don't even care that's 2 omega t, it's odd function, so going from negative t over 2 to t over 2, it's going to be 0. Okay. Now I also claim there's another one that's pretty easy to see. I claim this one also is pretty easy to see that it's 0. Well, how is that pretty easy to see? Well, again, we're integrating over a period. So you might say, well, I don't know what the period of the cosine function is because I don't know what omega is. I don't need to know that. Let's just draw one period of a cosine function. So I'll draw one period of a cosine function, or at least attempt to sketch it. So that's one period of a cosine function. And see if my sketch is all decent here. And I know it's from t over 2 to minus t over 2. I don't really necessarily care about that. I'm just putting in some bounds here. And it could be shifted. But what I'm really trying to say, this is one period of my cosine function. But if I integrate over one period, well, I've got this area here, and that area, and those down there, but they're all exactly the same. So they positive, positive, negative, so they cancel each other out. And so we get then that integral goes to 0. So really, we're left with a very simple integral of that the average power is simply equal to 1 over t integral from minus t over 2 to t over 2 of capital P dt. But then that would just simply be 1 over t capital P times little t evaluated at my endpoints, which now I'm belaboring this a tiny bit, because then you'd have t over 2 minus negative t over 2, but then wait a minute, t over 2 minus negative t over 2 is just t, canceling with this t, so we get P, capital P. Now why is that important for us here? Well, that means the average power is simply capital P, which remember was Vm Im over 2 cosine of theta v minus theta I. So that's what my average power is. Okay, great. So that's the average power coming out of, our outlets or something of that, or whatever the AC signal is. So that's great. But then that should bring up another question for us. So we've determined the actual physical meaning of capital P. That's the average power either being absorbed or delivered, depending on the direction of the currents and the sign of the power, if it's positive or negative. All right. Now, question is that should come to mind is then what is Q? Because we have Q here. Well, Q is what is called reactive power. And I'll put in quotes here, it's, quote, imaginary. Now, I hate using that term because it gets a bad rap. It's not imaginary, it's real power. It's just not real power that's available to us. And so let me kind of explain that a little bit in more detail here. P, which is average power, sorry, pause here, average power here. This is what delivers energy to a system. So when you compute the average power, that's literally like the average power going to your lamps or to your power supplies or to your AC motor, whatever. So that's literally the power that's used to deliver energy to a system, to turn a crank. Sometimes people almost want to think of it as physical energy. But then Q, which is reactive power, is not something you might say, oh, well, I want to get rid of reactive because it's not it's not useful. But this is actually this power helps regulate voltages in systems. And let's go a little bit more in detail. I mean, there's lots of reasons you have here, but if you have two coupled inductors, the reactive power is what maintains the voltages to generate the magnetic fields. You might say, well, what big deal about this? What's the big deal about this? Well, if those magnetic fields collapse, if we don't have those magnetic fields present, an inductor won't work. I mean, the whole point is an inductor's coupled, and you've got a current that's running through the inductor, which is giving rise to a magnetic field, and that magnetic field, because it's changing, induces a current in the secondary coil. So, but without reactive power, that process itself would not work. And so, yes, we don't get reactive power out on the other side of the transformer. We only get the average power back on the other side of the transformer, but we still need that reactive power in order for the transformer to operate. Okay. So let's talk a little bit here about actually a couple other things here. And so we have a couple other things we define here, something called the power factor. And there's going to be more than one way to compute these in this chapter here. So we abbreviate this sometimes as power factor as PF, and this is cosine of theta V minus theta I. And then we also have reactive factor, which is abbreviated RF, and this is actually the sine of theta V minus theta I. And there's something that's going to be, just seeing this equation here, you have your power factor squared plus your reactive factor squared has to equal 1. Now, that doesn't mean if you know the power factor you can compute the reactive factor. You can compute the magnitude, because these can be plus or minus, power factor and reactive factor. They can be both positive or negative. But we know then power factor squared plus reactive factor squared has got to equal 1, and that's just simply from the sine and cosine. So let's end this lesson here with actually going through an example of how we can determine some of these pieces of information. So let's look at an example here, and we're just going to have some boxes. So box A, and box B. And then I'll have plus minus VB plus minus VA, which of course they're the same, and then we'll have a current I here. So VA equals VB, which is simply going to be 100 cosine of omega t minus 45 degrees volts. And then I is simply going to be 20 cosine of omega t plus 15 degrees. So what are we going to find here? We want to find average power, reactive power, and the power factor, and then also the reactive factor. And I mean, this is honestly just a fairly straightforward computational problem here. So the average power here, if I look at this, this would simply be P is equal to 100 times 20 over 2 cosine of negative 45 degrees minus 15 degrees. And if you do that computation, you get 500. Now the units for power is still just watts, so we get 500 watts. Now, question is here, if we go back to this, does that mean that 500 watts is being delivered from A to B, or is it being delivered from B to A? Well, if we think about where the current arrow is going, it's going into the positive side of this voltage here. So that means B is actually going to have the positive 500 volts. So B is absorbing average power. Then let's go ahead and do what the reactive factor is, or not the factor, the reactive power. And again, that's a pretty easy computation here. This is just Q is equal to 100 times 20 over 2 sine of negative 45 degrees minus 15 degrees, which when you do that, you get negative 866. And now we should look at what the units are, and I hadn't mentioned this. We don't want to use watts, even though this is still current times voltage. The reason we don't want to use watts is because this is not average power. We want to be able to distinguish, even just by looking at the units, what we're talking about. And so what we do is we actually call these VAR, and the unit VAR is volt amp reactive, is the idea to think about it. A volt times an amp, which we know, yeah, volt times amps, that's watts, but we write it as volt times amps, and then an R for reactive, because that tells me that this is a reactive power. And since it's negative, that means A is absorbing reactive power. Now if we compute the power factors here, we get that cosine, of negative 45 minus 15 degrees, these are both degrees, and this is equal to 1/2. And then my reactive factor is simply the sine of negative 45 degrees minus 15 degrees, I should say it's 0.5, which is negative 0.866. Now, again, if you add these up, you get 1. Now, what these power factors indicate, is, well, since power factor being 0.5 here, that means that, we're actually not, the total power in the system, we're actually not getting a lot of that back as, real power being able to turn a crank. Now, you can't say, oh, we're getting half of it back. That's not what the power factor tells you, but that gives you some useful information. All right, so we're going to end this lesson here, and then the next lesson we're going to continue talking about power factors and things of that nature. Actually, I think we're going to talk about RMS value. And just to kind of give you a heads up, phasors and all of our phasor analysis is going to come back into play. We're just trying to understand this idea of average and reactive power.